recording. And it looks like everything is working. All right. So today we are going to start section 9.4, which covers the limit comparison test. Okay. With the limit comparison test, let's say if we had some series we'll call a sub n that's greater than or equal to 0, and some series we'll call b sub n that's greater than or equal to 0. For every n greater than or equal to some very large value that we will call our uppercase N, first we know that if the limit of a sub n divided by b sub n as n approaches infinity is equal to some limit value L. But we know that that L is not 0. And then we know that the series from n equals 1 to infinity of a sub n and the sum from n equals 1 to infinity of b sub n either both converge or both diverge. The next is that what if it does happen to equal 0? So if the limit of a sub n divided by b sub n as n approaches infinity equals 0, and we know that the sum from n equals 1 to infinity of b sub n converges, then a sub n also converges. Excuse me. Okay. And we know that if the limit of a sub n divided by b sub n as n approaches infinity is equal to infinity, and the sum from n equals 1 to infinity of b sub n diverges, then we know the sum from n equals 1 to infinity of a sub n will also diverge. Now, for a lot of these, it's very helpful to remember the geometric series because you will be using it for a lot of these problems. And just as kind of a reminder, the sum from n equals 0 to infinity, a times r to the power of n, or you can rewrite it as the sum from n equals 1 to infinity, a times r to the power of n minus 1. And they both have the same exact form. A plus a times r plus a times r squared. It keeps on going in that form. Okay, and we know that if the absolute value of r, move that over a little bit, make sure I can fit it all on one line. That's if the absolute value of r is less than 1, the series converge. Now, if the absolute value of r is well, you might as well say less than 1, then the series will diverge. All right. So let's say, for example, we got to put this up. Put that over here. So let's say, for example, if we let the sum from n equals 1 to infinity, a sub n equal the sum from n equals 1 to infinity of 8 times square root of n divided by n to the 8th power plus 6. And the sum from n equals 1 to infinity of b sub n is equal to the sum from n equals 1 to infinity of 1 divided by n to the power of 15 divided by 2. So we want to compute the limit for both of those. Move that a little bit, give that a little more space. There we go. By compute the limit, we just want to know converge or diverge. Okay. So now we just want to take the limit as n approaches infinity of your a sub n divided by your b sub n. No, that's just going to equal the limit as n approaches infinity. 8 times square root of n divided by n to the 8th power plus 6 divided by, and you can just call that 1 over n to the, I was going to rewrite it, but I'll write it the original way first, divided by 1 over n to the 15 halves power. So just to make this a little simpler to read, we're going to multiply the numerator and denominator by the reciprocal of the denominator. So we're going to multiply the numerator and denominator by n to the 15 divided by 2 power. Okay, where in the denominator, they cancel out and just become 1. So we have the limit as n approaches infinity of 8 square root of n times n to the 15 divided by 2 power divided by n to the 8th power plus 6. Okay, we can actually combine these two. And we'll do that over here on the side. So if we have the square root of n times n to the 15 divided by 2 power, and we can rewrite this as n to the 1/2 power times n to the 15 divided by 2 power. We can rewrite that again, since you have the same base, you can just add the exponent. 1/2 plus 15 divided by 2. Just n to the 16 divided by 2 power, or just n to the 8th power. So if we combine those two, we just end up with the limit as n approaches infinity of 8 times n to the 8th power divided by n to the 8th power plus 6. Once it's in this pretty simplified form, all we have to do is divide each term by n to the 8th power. Or multiplying it by 1 over n to the 8th power, same thing. So we have the limit as n approaches infinity of 8 times n to the 8th power divided by n to the 8th power divided by n to the 8th power divided by n to the 8th power plus 6 divided by n to the 8th power. All right, well, we can see these n to the 8th powers cancel each other out. So does these two. I'll make that equal sign just to keep it consistent. So that gives us the limit as n approaches infinity of 8 divided by 1 plus 6 divided by n to the 8th power. So if we take the limit of each term, the limit of 8, the limit of a constant is always just a constant, divided by the limit of 1, which is just 1, plus the limit of a constant divided by a number getting bigger and bigger is always going to be 0. So it's just 8. Okay, so we can see here that the limit as n approaches infinity, make that n a little neater. A sub n divided by b sub n equals 8, which does not equal 0. Okay, they either both converge or both diverge. So we know it passes that test. So now all we have to do is pick one of them and find out whether they both converge or both diverge. The easiest one out of the two would be the sum from n equals 1 to infinity of 1 over n to the 15 divided by 2 power. Okay, so all this tells us is that either both converge or both diverge, just by taking the limit of their quotient. Okay, so this one, using the p-series test, that p is equal to 15 divided by 2, which is greater than 1. So this one will diverge. So we know that a sub n, and well, we can say the limit as n approaches infinity and for a sub n and b sub n, both diverge. Bring that over a little bit. There we go. Okay, so everything we did before this last step just told us whether or not they will both converge or diverge. So the fact that the limit didn't equal 0 just meant that if you found the limit of one, you found the limit of both. All right, any questions on that one? Okay. Okay, so let's say, for example, if we wanted to let the sum from n equals 1 to infinity of a sub n equal the sum from n equals 1 to infinity of 2n to the 4th power minus 12n squared plus 16 divided by 4n to the 6th power minus 24n to the 4th power plus 32n squared. And the sum from n equals 1 to infinity of b sub n is equal to the sum from n equals 1 to infinity of 1 over 8 n squared. So with this one, we just want to compute the limit as n approaches infinity of a sub n divided by b sub n. Okay, so we know that the limit a sub n divided by b sub n as n approaches infinity is equal to the limit as n approaches infinity of 2n to the fourth power minus 12n squared plus 16 divided by 4n to the sixth power minus 24n to the fourth power plus 32n squared. Oh, there we go. And that whole thing divided by 1 over 8n squared. So of course, first thing we want to do, get rid of that fraction in our denominator. So we multiply the numerator and denominator by its reciprocal. So we'll multiply them both by 8n squared. These two just cancel each other out and become 1. So we have the limit as n approaches infinity. In our denominator, we're just going to go ahead and distribute that 8n squared to each term. So we have 16n to the sixth power minus 96n to the fourth power plus 128n squared divided by 4n to the sixth power minus 24n to the fourth power plus 32n squared. So to simplify this even more, we find the term with the largest variable exponent, which is n to the sixth power. So we divide each term by n to the sixth power. So we have the limit as n approaches infinity of 16n to the sixth power divided by n to the sixth power minus 96n to the fourth power divided by n to the sixth power plus 128n squared divided by n to the sixth power divided by 4n to the sixth power divided by n to the sixth power minus 24n to the fourth power divided by n to the sixth power plus 32n squared divided by n to the sixth power. Okay, so if we simplify it, it's just the limit as n approaches infinity. These two into the sixth power cancel out, so does these two. So we have 16 minus, we have 96 divided by n squared. Plus 128 divided by n to the fourth power. And all of that divided by 4 minus 24 divided by n squared plus 32 divided by n to the fourth power. So now we take the limit of each term and move this down a little bit so we have enough room. So we have the limit as n approaches infinity of 16, and the limit of any constant divided by a number getting bigger and bigger is always going to be 0. So a constant dividing by a number getting infinitely bigger is 0. Divided by the limit of 4 is 4. Here, the limit of a constant divided by a number getting bigger and bigger is still going to be 0. Plus constant dividing by an infinitely bigger number is just going to be 0. So we have the limit of 16 divided by 4, which is just the limit of 4, which is 4. Now, this one didn't want you to find out whether it converge or diverge. It just wanted you to find the limit, which is exactly what we did. And they actually told you which limit they wanted you to find. So they usually point out what they want the answer to look like. So, all right, any questions on that one? All right. Okay, so let's say we have we're using the limit comparison test. With a geometric comparison series of the sum from n equals 1 to infinity of 2 to the power of n divided by 3 to the power of n. Determine if the series below will converge or diverge. And that's the sum from n equals 1 to infinity, 2 to the power of n plus 9, divided by 3 to the power of n. So since we want to use the limit comparison test, we'll let the limit as n approaches infinity, a sub n divided by b sub n. Let me clean up that a. Looks a little too much like a 9 to me. There we go. We'll just let that equal the limit as n approaches infinity, 2 to the power of n plus 9 divided by 3n divided by 2n divided by 3n. Okay, so all we did here, we just let that equal our a sub n, and this one equal our b sub n. Or you could have flipped it around if you wanted to. It would have been your call. But I just happened to pick those two. Okay, so of course now we want to simplify it. So I'm going to have to shorten up my arrows a little bit. Actually, I'll just move them around because I don't want to have to rewrite the whole thing. So this is our a sub n and this is our b sub n. So to simplify it, we multiply it by the reciprocal of our denominator. So we're going to multiply it. But for this one, we don't want to get rid of it completely. At least we don't have to. So we can just multiply by 3 to the power of n. Because that'll simplify the numerator. And this one, it'll only give a single factor in our denominator, which is good enough. So this 3 to the power of n cancels out with this one, and this one cancels out with this one. So we end up with the limit as n approaches infinity, 2 to the power of n plus 9 divided by 2 to the power of n. So I wrote that as 2 times n. Clean that up a little bit. There we go. So just like we did before, we wanted to kind of simplify this a little bit more. We can divide each term by 2 to the power of n. So that gives us the limit as n approaches infinity, 2 to the power of n divided by 2 to the power of n. Actually, we can do that a little bit easier than rewriting it that way. We can just separate them all. Save a little bit of work. Because we'll get the same answer. So if we separate, we just have 2 divided by n divided by 2 divided by n plus 9 divided by 2 divided by n, which is the same thing. Don't know why I didn't see that sooner. So 2 to the power of n divided by 2 to the power of n is just 1. So if we take, and you can put parentheses around the whole thing if you want to, you don't have to. But if we take the limit of both terms, we have the limit of 1 is just 1, plus the limit of a constant divided by a number getting bigger and bigger and bigger and bigger is just 0. So this limit is just 1. But we know that it does not equal 0. Which means they both converge. or both diverge. Okay. Well, for this one, they wanted us to use the limit comparison test with geometric comparison. So what we're going to do is we're going to use the geometric series on this series. Okay, so we can take that sum from n equals 1 to infinity of 2 to the power of n divided by 3 to the power of n, and we're going to rewrite it as the sum from n equals 1 to infinity of 2 divided by 3 to the power of n. Okay, but remember, let me go back, how many pages? Right, the very first page. For the geometric series, if it starts at 1, then your r has to be to the power of n minus 1. So we have to rewrite this in the power of n minus 1. Okay, so one way to do it sum from n equals 1 to infinity is we could get that denominator and move it up to the numerator and give it an exponent of negative 1. So 3 to the power of negative 1. Oops. Yeah, that looks okay. Same thing with the numerator. We can move it down to the denominator and give that an exponent of negative 1. So 2 to the power of negative 1. And both to the power of n. Okay, so if we take those, we have the sum. Should I write it? I'll write it next to it. Try to get as much space used up and not have to put this on a second page. So you have the sum from n equals 1 to infinity. 3 to the negative 1 power divided by 2 to the negative 1 power to the power of n. Okay. So what we're going to do is we're going to multiply it by 2/3 times 3/2, which is just 1. This 2/3, we're just going to factor that right on out to the front. Oh, a little too far with the factoring. So I'm going to factor it right out there. So that's going to give us, move it over a little bit, 2/3 times the sum from n equals 1 to infinity of 3 to the negative 1 power divided by 2 to the negative 1 power to the power of n divided by 3/2. Okay, so if we combine these two, actually, I went about that the very long way. Oh well, we'll find it. Go get it at the end. Could have skipped a few steps, but the sum from n equals 1 to infinity. If we multiply the exponent, that gives us negative 3 to the power of negative n. Hey, when I see things too late. Divided by 3 to the power, 2 to the power of negative n. And just erase it. Make it a little neater. Times 3 divided by 2. I just made extra work. And like I said, I didn't even realize it till right now, but you'll see it in a second. So we have 2/3 times the sum from n equals 1 to infinity. So if we combine those two, we have 3 to the power of negative n plus 1 divided by 2 to the power of negative n plus 1. And the extra work was because I didn't really have to do that. I probably could have worked around it because now we're going to have to move this back up to the numerator and take the negative, which would make that n minus 1. Oh, forgot my 2/3. Yep, sometimes you don't see the shortcut until later. To infinity of 2 to the power of n minus 1 divided by 3 to the power of n minus 1. Okay, so we take our answer here, and I'll just move this over here and put it inside a little box. That sum from n equals 1 to infinity, we can rewrite that as 2/3 to the power of n minus 1. Like I said, I did a lot of unnecessary work on that one. Which means we can make that 1 times this if we wanted to rewrite it. Which means that our absolute value of r is equal to 2/3, which is less than 1. So we know that this one, using the geometric series test, converges. So both converge. Yeah, I really wish I would have caught that before. Probably could have cut out 2 or 3 of those steps, but we ended up with the right answer at the end, so no big deal. All right, any questions on that one? Okay, so we use the limit comparison test. Now we are going to use the direct comparison test. Oh, anyone still writing? All right. Okay, so with the direct comparison, it's just like the name says, you're directly comparing the two series. Okay, so I'll give you a visual representation, then I'll give you the definition. Okay, so what if we let two series, let's say just less than, not less than or equal to. We have two series where the series a sub n is less than the series b sub n, and they're both greater than 0. And that's for all of your n values, from n to infinity. I mean, from 1 to infinity, rather. So that means if we have our series a sub n, and we get our series and all the values for our series, kind of make those points. If it's always less than b sub n, that means b sub n will also diverge if a sub n is diverging. So if a sub n goes all the way up and diverge, so does b sub n. Same thing if b sub n converges. If b sub n converges, I'll say to 0 just because it's already there. Since a sub n is less than b sub n, then a sub n will also converge. Excuse me. And this idea gives us our direct comparison test. Okay, so what if we let just this same stipulation up here, a sub n be less than b sub n? Then if the series from n equals 1 to infinity of b sub n is convergent, then a sub n is also convergent. And I should have switched these around. This is actually number 1, and this one will be number 2. Make that a little neater. For the second comparison test, the sum from n equals 1 to infinity of a sub n is divergent, then the sum from n equals 1 to infinity of b sub n, that series is also divergent. sure I have enough paper. Yeah, it should be okay. Make sure I have enough. Here we go. All right. So let's say, for example, if we wanted to determine if the series below converges or diverge using the direct. And sometimes they'll call it the direct limit comparison test or just the direct comparison test, same thing. Okay, and the series is the sum from n equals 4 to infinity of n factorial divided by n minus 3. Okay, so looking for the convergence or divergence for a somewhat tricky looking series, you don't want to actually deal with that if you can avoid it. So what you want to do is you want to compare it to one that's a whole lot simpler. And what I normally try to do is use the p-series test because it's the easiest. So use the p-series test. When possible, bless you, because it is the simplest. You're just comparing exponents. I mean, you can use whichever other one you like, but this is my personal preference. Okay, so what if we let a sub n equal n factorial divided by n minus 3? And b sub n equal 1 over n, when n is greater than or equal to 4, since that's our domain. So if you want to just double check, you'd always plug in values of n being greater than or equal to 4. So we know that when n is greater than or equal to 4, then n factorial over n minus 3 is greater than or equal to 1 over n, which is greater than or equal to 0. Or you can flip it around and just say 0 is less than or equal to 1 over n, which is less than or equal to n factorial divided by n minus 3. Okay. So just putting it in this form know 0 is less than or equal to a sub n is less than or equal to our b sub n. So if a sub n is divergent, and so is b sub n, because if a sub n goes up to infinity, then this one will go up to infinity also. So if we look at the sum from n equals 4 to infinity of 1 over n, remember that's just 1 over n to the first power. So we could rewrite that as 1 over n. Let me write that a little bit bigger. About to write the fourth power. And to the first power. There we go. And with the p-series test, we know that when p is less than or equal to 1, it's divergent. So if our a sub n is divergent, so is our b sub n. So we know that the sum from n equals 4 to infinity of n factorial divided by n minus 3 is also divergent by the direct comparison test. And again, that's why I always use well, at least not always, but whenever possible, I try to use the p-series test. For no other reason than pure convenience. All right. So let's say, for example, let's say if we wanted to determine if the series below is convergent or divergent using direct comparison. And we have the sum from n equals 1 to infinity of 7 divided by the square root of 16n squared minus 2. Okay. Now for one like this, the first thing I would do is look at the lead term. For n is greater than or equal to 1. Okay, so we're looking for a series to compare it to. If we have 7 divided by the square root of 16n squared minus 2, we know that's greater than or equal to 7 divided by the square root of 16n squared. Okay, so think about when the denominator is just a little bit smaller, it's bigger. That's like saying 7/8 is bigger than 7/9. Okay, so that means we know that 7 divided by 16n squared minus 2, that square root is greater than or equal to 7 divided by the square root of 16n squared is just 4n. So we know 7 divided by that square root of 16n squared minus 2. If we simplify that a little bit more, we know 7 over 4 times 1 over n. Okay, so we could rewrite this since 7 divided by the square root of 16n squared minus 2 is greater than 7 over 4 times 1 over n. That means 7 over 4 times 1 over n is less than this one. So we can rewrite it as 0 is less than 7 over 4 times 1 over n, or you could just say 1 over n is less than 7 divided by the square root of 16n squared minus 2. Because you want to get it in the direct comparison form. So you want it in the form of 0 is less than a sub n is less than b sub n. So we know this is your a sub n, so we're going to let this be your b sub n. Okay, so using a sub n, again, using the geometric series, we know that, not geometric series, p series, since that one's a little easier. So if we have 7 over 4 times the sum from n equals 1 to infinity of 1 over n to the first power, we know that when p is less than or equal to 1, it diverges. So we know that if this is divergent, then this is also divergent. So we know that the sum from n equals 1 to infinity of 7 divided by the square root of 16n squared minus 2 also diverges. All right, any questions on that one? Okay, looks like everyone's done writing. Okay, so what if we wanted to determine if sum from n equals 2 to infinity of natural log of n divided by 3n to the third power is convergent or divergent using direct comparison. Okay. So again, the whole start of this one is trying to figure out what you're going to compare it to. Well, if we look at it, we can kind of pick somewhere to start. Sometimes you might pick some place that's not helpful to start. Sometimes you might pick the perfect comparison. It's a process. Okay, so we know that the natural log of n is less than or equal to n for n greater than or equal to 2. Natural log of 2 is less than 2. Natural log of 3 is less than 3. So forth and so on. So if the natural log of n is less than or equal to n, then we know that the natural log of n divided by 3n to the third power is less than or equal to n divided by n. So 3n to the third power. So if we simplify that even more, the natural log of 3n to the third power is less than or equal to 1 over 3 n squared. So once again, we can rewrite this. And let me make enough room for my rewrite. As 0 is less than the natural log. Oh, forgot my n. Let me write this a little smaller. It'll look a little bit out of place. Natural log of n divided by 3n to the third power is less than 1 over 3n squared. Okay, so we can see here that this is in the form 0 is less than a sub n is less than b sub n. Okay, so we'll let our b sub n equal 1 over 3n squared. So if we rewrite that, we have the sum from n equals 2 to infinity. We can actually factor out the 1/3. That really doesn't do us any good being in there. Of 1 over n squared. That looks like an h. Let me change that till it looks a little bit better. 1 over n squared. There we go. Okay. And we know this converges because the p-series test, we know that p is equal to 2, which is greater than 1. So we know it converges. So since B sub n converges, we know that A sub n will also converge. So we know that the sum from n equals to infinity of natural log of n divided by 3n to the third power is also convergent. So the hardest part of this is finding a series to compare it to. And this part here is just my thought process in finding a series to compare it to. Then once you find a series to compare it to, then you do your convergence or divergence if you can using the direct comparison theorem. All right, any questions on that one? And again, I try to compare it to a series in the simplest form possible. I try not to overcomplicate it. All right, anyone still writing? Okay. So what if we wanted to determine if the sum from n equals 1 to infinity of 1 over the square root of n minus 3 is convergent or divergent? The IE using direct comparison. And I'll say diverges and not divergent. Sounds a little bit better. So again, we're going to start off by finding our series to compare it to, and we're going to keep it as painless as possible. So the first thing we're going to notice is that if we have 1 divided by the square root of n minus 3, well, that's greater than or equal to 1 divided by the square root of n. Okay, so we can always just flip these around. So we can rewrite it as 0 is less than 1 over the square root of n, which is less than 1 over the square root of n minus 3. Okay, so right now this is in the exact form we need. 0 is less than a sub n, which is less than b sub n. So we know that if we take the series from n equals 1 to infinity of our a sub n, we could rewrite it. I'll write it the original way first. That's equal to the sum from n equals 1 to infinity of 1 over n to the 1/2 power. Like I said, and this is why we just take the simplest comparison possible. Because all we have to do is using the p-series test, our p is equal to 1/2, which is less than 1. You know, when that p is less than 1, it diverges. So since your a sub n diverges, your b sub n is also divergent. So we know that the series from n equals 1 to infinity of 1 over the square root of n minus 3 also diverges. If you pick the wrong comparison the first time, then just grab a second comparison. It's not a all or nothing thing. You can do the first time and end up with the wrong comparison, then pick another one and end up with the right answer. It's just a process. So don't get frustrated if you have to do this more than once. It's kind of a rite of passage. Until you get comfortable, then you'll be able to kind of look at them and say, okay, I can pick this one. Okay, I can pick that one. And then it kind of comes to you. But starting off, it's very, very common to pick the wrong one every once in a while. Or you might get lucky and pick the right one 10 times in a row. You never really know. That's the fun part. So what if we wanted to determine if the series 1 divided by 2 plus 3 to the power of n is convergent or divergent? Excuse me. Now, because we have an exponent to the power of n, we probably can't use the p-series test, but that doesn't mean it has to be any more difficult, as long as you know other tests. But first thing we're going to notice is that 1 divided by 2 plus 3 to the power of n is less than 1 over 3 to the power of n. And again, if you're ever confused as to whether it's less than or equal to, just plug in a few values. If we plug in n equal 1, we know 1/5 is less than 1/3. So that's for n is greater than or equal to 1. Probably should have put all of that in a little box, so I'll add that to the box. Okay, so we can rewrite this as 0 is less than 1 over 2 plus 3 to the power of n is less than 1 over 3 to the power of n. Which is the exact form we need it in. So we let our b sub n equals 1 over 3 to the power of n. Okay. Now, the thing is, if this diverges, then it doesn't help us here. But if this converges, then we know that this one converge. So if the larger one is divergent, then it doesn't really mean anything for this one. So this one has to converge. So I guess that's why I said that if you want to, if you end up picking the wrong one, it's no big deal, because you may say, okay, I want to prove this is divergent. So if this one ends up being divergent, then it doesn't help us here. So then you'd have to pick another one and prove that it's convergent. So like I said, it's an entire process, and your brain kind of gets used to it if you see it enough times. Okay. So now we want to see if this will be convergent. Okay, so if we take the sum from n equals 1 to infinity of 1 over 3 to the power of n, we could rewrite that as the sum from n equals 1 to infinity. That 1 over 3 to the power of n, we can rewrite that as 1/3 to the power of n. 1 to the power of n is 1, 3 to the power of n is our 3 to the power of n. And we can just multiply by 1. You don't have to, but I'll do it anyway just to put it in the right form. So now we have it in the geometric series form. The sum from n equals 1 to infinity, a times r, but it starts at 1, so we have to put this to the power of n minus 1. Okay, so again, first thing we're going to do is we're going to get our minus 1. So we're going to multiply this by 1 to the negative. I guess you can say 1/3. I don't want to overcomplicate it again. This will be better. I think this will be a quicker. 1 to the negative 1 power over 3 to the negative 1 power. And 3 to the negative 1 power times 1 to the negative 1 power. So just the reciprocal of itself. Okay, so if we get that 3 to the negative 1 and factor that right out to the front, 3 to the negative 1 over 1 to the negative 1. We have our 3 to the negative 1 times 1 to the negative 1 power times the sum from n equals 1 to infinity of 1/3 times n, or 1/3 times n, 1/3 to the power of n. And if we multiply these two together, actually I could have just moved that up there. I don't know why I'm making that same too much work habit today. Okay, so if we multiply these two together, we have, there we go. There we go. Should have crossed that out after I factored it. I was getting ready to compare the wrong ones. Okay, so if we have 1 to the power of n times 1 to the power of negative 1, that's 1 to the power of n minus 1. If we have 3 to the power of n times 3 to the power of negative 1, that's 3 to the power of negative n, of n minus 1, not negative n. So we can just rewrite that way. And that 3 to the negative 1 and 1 to the negative 1, we could just rewrite that as 1/3 if we wanted to. I just did that just for this step. we can say 1 times 1/3 to the n minus 1 power, which puts us exactly in the form that we need. Okay, so we could see here that our r is equal to 1/3. Because remember our geometric series, we want the absolute value of r. Now I'll put it over here. The absolute value of r is equal to the absolute value of 1/3, which is 1/3. And 1/3 is less than 1, so we know it converges. So if your b sub n converges, then your a sub n also converges. So I'll put that down here instead of over there. So we have the sum from n equals 1 to infinity of 1 divided by 2 plus 3 to the power of n also converges. All right, any questions on that one? Okay, now these, like I said, are tricky because sometimes they will be nice and give you the series to compare it to, but that's usually just at the beginning. After that, they kind of give it to you like this and have you find your own. Like I said, it's the finding your own that's the tricky part. But once, like I said, once you get comfortable with it, it gets a little bit easier each time. All right. Anyone still writing? All right. Okay, we move these out of the way. Put these in order so I don't mix anything up. Here we go. Okay, so now we're going to look at section 9.5, which is the alternating series test. And I will bet money a bunch of you probably asked yourself, how many tests are there? There are quite a few, unfortunately. But with the alternating series test, let's say if we let a sub n be a series that's greater than 0. Okay, now with the alternating series test, we'll make that capitalized. That's if you have the series from n equals 1 to infinity of negative 1 to the power of n of a sub n, or the sum from n equals 1 to infinity of negative 1 to the power of n plus 1 of a sub n. Okay, so in either one of those forms, those converge if the following conditions are met. Okay, the first condition is that the limit as n approaches infinity of your a sub n is equal to 0. And the second condition is that a sub n plus 1 is less than or equal to a sub n for every value of n. Or in other words, non-decreasing. So we have to say non-decreasing only because it can be constant. It just can't decrease. So it can either increase or it can remain constant as long as it's not decreasing. All right, anyone still writing? Okay. So let's say, for example, if we wanted to determine the convergence or divergence of the series, the sum from n is equal to 1 to infinity of -1 to the power of n plus 1 times 1 over n. Now this one will go, if you plug in values of n, it'll go from positive, negative, positive, negative, positive, negative, basically alternating signs. Okay, so we want to know, just to kind of give you an idea, if they're alternating signs, if they're both alternating towards a specific value, or they're alternating signs and going off into its own little area. Okay. So all we have to do is look at the two conditions. The first condition, if we let a sub n equal our 1 over n, the first condition is that the limit of a sub n as n approaches infinity, it has to equal 0, which in this case, the limit of 1 over n as n approaches infinity, we have a constant divided by a number getting bigger and bigger and bigger, so that limit is 0. So that first condition is met. And the second condition, it has to be non-decreasing. So a sub n plus 1 has to be less than or equal to a sub n. Okay, well, we know that a sub n plus 1, well, that's just 1 over n plus 1. Just replace n with n plus 1. And that's less than or equal to 1 over n. which is true for every value of n greater than or equal to 1. Okay. So this one is true. So since, yes?
How would it be less than if you're adding 1 to
it?
How would the 1 over n plus 1 be less than 1 over n? Because aren't you adding 1?
Yep, you're adding 1, but to the denominator, think of it as, like I said, I'll normally just plug in a value. So let's say if you plug in n equals 2. We know that 1/3 is less than 1/2.
Gotcha.
You see it? I know it doesn't look right.
Yeah.
That's why I always say plug in a value just to make sure, because it's like, it doesn't look right. But yep, that's why I do that. Okay, so we know that since both conditions are met, and we know that the sum from n equals 1 to infinity of -1 to the power of n plus 1 of 1 over n converges by the alternating series test. Yeah, I'll just circle the whole thing. Excuse me. All right. Any questions on that one, or any other questions? All right. Oops. All right, so let's say we wanted to find the convergence or divergence. Using the alternating series test. And you have the sum from n equals 1 to infinity, -1 to the power of n plus 1 times 11n divided by 8n plus 6. Okay, so we're going to let our a sub n equal 11n divided by 8n plus 6. Okay, so now we have to test the first condition. This limit has to equal 0. So we take the limit as n approaches infinity of our a sub n. Which is the limit as n approaches infinity of 11n divided by 8n plus 6. Okay, so to simplify this even more, We're going to divide each term by the highest variable and exponent, which in this case is n to the first power. So it's 11n divided by n, divided by 8n divided by n, plus 6 divided by n. Okay, so we know those n's cancel out and those n's cancel out. So we have the limit as n approaches infinity of 11 divided by 8 plus 6 over n. Okay, so if we take the limit of each term, that's equal to the limit as n approaches infinity of the limit of 11 is just 11 over the limit of 8, which is 8, plus the limit of a constant divided by a number getting bigger is just 0. So actually didn't even need the limit anymore after we applied it to each term. So it's just 11 over 8. So this limit does not equal 0. So it doesn't tell us anything other than the fact that we can't use the alternating series test. Okay, so with that one, it would give us an inconclusive answer, but it doesn't mean we can't use another test. We just can't use this particular one because it doesn't meet the conditions. Okay, so what if we want to use the test for convergence? I mean divergence. Okay, so we know that the limit as n approaches infinity, 11n divided by 8n plus 6 is equal to 11 over 8, which we know does not equal 0. So by the test for convergence, it diverges. All right, any questions on that one? All right, leave that up for a few more seconds. Let everyone finish writing. All right. Do the next one. Okay, so what if we wanted to determine if the sum from n equals 1 to infinity of -1 to the power of n plus 1 times e to the power of 2n divided by 7 converges or diverges using the alternating series test. And again, you'll always know the alternating series because you'll see that -1 to the power of n or to the power of n plus 1. I'm not saying the alternating series test is the only test you can use, but you'll just be able to recognize an alternating series. Okay, so remember the first step. You take the limit as n approaches infinity of your a sub n. Okay, so our a sub n, let me write that, is equal to 1/7 times e to the power of 2n. I just factored out the 1/7. So we can rewrite that as 1/7 times the limit as n approaches infinity of e to the power of 2n. Oops, straighten that up a little bit. There we go. Okay, so e to the power of 2n, as n gets bigger and bigger and bigger, that whole thing just keeps getting bigger and bigger and bigger. So we know that limit is infinity, which we know is not equal to zero, so it fails the first condition of the alternating series test. So it fails the first condition of the alternating series test. And really, if you have the test for divergence kind of known or memorized, you can just tell by what your answer is here whether or not it converges or not. So usually that's my go-to, is the test for divergence. Whenever it fails, I just normally hop to that whenever possible. So using the test for divergence, the limit of e to the power of 2n as n approaches infinity, I've got that 1/7, is equal to infinity, and that shows that it's divergent. All right, any questions on that one? Okay, so it's helpful to have a extra test in your back pocket. That's why we have so many of them, because not all of them work in every situation, so it helps to have backups. Okay, so what if we wanted to determine if the series 1/4 minus 1/16 plus 1/64 minus 1/256 plus 1/1024 minus, and it keeps on going in that pattern. If it converges or diverges. Using the alternating series test. Okay, so the first thing we have to do is put this in the right form to find our series A sub n. Okay, so what we're going to do is we're going to look for a pattern. Okay, so that 1/4, we can make that 1/4 to the first power. Minus that 1/16, we can make that 1/4 squared. That 1/64, we can make that plus 1/4 to the third power. Minus 1/4 to the fourth power. Plus 1/4 to the fifth power, and so forth and so on. Okay, so just using that pattern, we can see that this will give us the sum from n equals 1 to infinity of -1 to the power of n plus 1 of 1/4 to the power of n. So if your first term is positive, you're going to want to use -1 to the power of n plus 1, because if you plug in n is equal to 1, it'll be -1 squared, which is positive. But if this would have been negative, then you would have -1 to the power of n. So that's -1 to the first power is negative. So that first term would have been negative. Okay, so we can see here, just from us being able to find that pattern, that a sub n is equal to 1/4 to the power of n. Okay, so now we test the conditions. We have the limit as n approaches infinity of our a sub n. So first condition is that has to equal 0. So that's equal to the limit as n approaches infinity of 1/4 to the power of n. Well, we can see there we have a constant divided by a number that's getting bigger and bigger and bigger and bigger and bigger. So we know that that limit is always going to equal 0. So the first condition is passed. Now your second condition is that a sub n plus 1 has to be less than or equal to a sub n. It has to be non-decreasing. Which means that 1 over 4 to the power of n plus 1 has to be less than or equal to 1 over 4 to the power of n. For every value of n greater than or equal to 1. And just plug in values. If you plug in n is equal to 1, 1 over 16 is less than 1/4, which is true, and you can keep on going. So we can see that it's always true. Okay, so we know that both conditions are met, so we know that that series converges. So both conditions are met, so we know that the sum from, move that up a little, n is equal to 1 to infinity of -1 to the power of n plus 1 times 1 over 4 to the power of n converges. Excuse me. All right. I'm sorry, was anyone still writing that last one? I grabbed it without asking. All right. So let's say if we wanted to determine if the series two minus 3 over 2 plus 6 over 5 minus 1 plus 6 over 7 minus, and it keeps on going and going in that pattern, converges or diverges using the alternating series test. Now with this one, again, first step, easier said than done, is find the pattern. This is also one of those things where it's going to be a lot of trial and error on some of them. Some of them you'll figure out right away. Some of them it'll take you 5 chances to figure out the pattern. But so let's say I'll just rewrite it: 2 plus 3 over 2. Leave a little bit of space between each one, just so I can make little notes. Plus 6 over 5 minus 1 plus 6 over 7 minus, and it keeps on going. Okay. Now with me, the first thing after I tried a couple of things that didn't work, I noticed that these two have a numerator of 6. So I figured those who have a numerator of 6, maybe that's because it's the simplest form and it can't be reduced anymore. So I'm thinking if I give the rest of these a numerator of 6, will it show a better pattern? So I'll multiply this one by 3 over 3. This one by 2 over 2. That one I left alone. This one by 6 over 6. So this gave me 6 over 3 minus 6 over 4 plus 6 over 5 minus 6 over 6 plus 6 over 7 minus, and kind of got the pattern there. Okay, so this gives us, I'll put it below it just to make sure I have enough room. So we have the sum from n equals 1 to infinity of -1 to the power of n plus 1 times 6 divided by n plus 2. Because remember, our very first term has a denominator of 3. So we can see just right there that our a sub n is equal to 6 divided by n plus 2. And clean up that 6 a little bit. Here we go. So now that we have our series in the right form, we can look at our conditions. We have the limit of a sub n as n approaches infinity, which is the limit of 6 divided by n plus 2 as n approaches infinity. Well, we have a constant divided by a number getting bigger and bigger, so we know that limit is 0, so that condition is met. And we have our second condition, it has to be non-decreasing. So your a sub n plus 1 has to be less than or equal to your a sub n. So that means our a sub n plus 1 is just 6 divided by n plus 1 plus 2. Uh-oh, made that a little too big. 6 divided by n plus 1 plus 2 is less than or equal to your a sub n, which is 6 divided by n plus 2. So if we rewrite it, n plus 1 plus 2 is just n plus 3. So we have 6 divided by n plus 3 is less than or equal to 6 divided by n plus 2. Okay, which we can see is true for all n greater than or equal to 1. Okay. Like I said, you can always plug in a few test values just to make sure. Plug in n equals 4. 6 divided by 7 is less than 6 divided by 6, which is 1. So we know that's true. Plus, if you keep on going, it does the same thing. Okay, so we know the second condition is met. So again, we go, since both conditions are met, that means that our series, and instead of writing it in the long expanded way, I'll just write it as our nice little condensed version. Sum from n equals 1 to infinity, -1 to the power of n plus 1 times 6 divided by n plus 2 converges. All right, any questions on that one? All right. Let's see, example. Yep. Okay, so we'll do one more like that one, then we'll move on to another one. So we want to determine if the series -1/15 plus 1/8 minus 3/17 plus 2/9 minus 5/19 plus et cetera, and so on. Converge or diverge. Using the alternating series test. Okay, so again, first thing you want to try and do is find the pattern. Again, easier said than done sometimes, but it is the first step. And I'll go ahead and rewrite it. So -1/15 plus 1/8, make that 5 a little bit neater than that, minus 3/17 plus 2/9 minus 5/19 plus, and it keeps on going. Okay. So again, after a few failed attempts, kind of looked at it again and noticed here you have a numerator of 1, 3, and 5. So I wondered if I make this numerator 2 and this one 4, would that pattern be a little easier to figure out? Okay, so we have -1/15 plus, to make this numerator 2, multiplied by 2/2, so that's 2/16, minus 3/17, plus, to make this one 4, multiplied by 2/2, so we have 4/18, minus 5 over 19, which kind of made it a little easier. So that's equal to the sum from n equals 1 to infinity. And remember, when that first term is negative, you want to make that negative 1 to the power of n. Times n divided by n plus 14. Okay, so we finally found our a sub n is equal to n divided by n plus 14. Okay, wait a few seconds, let everybody kind of catch up. Okay, so we know our first step is we want to find the limit, and we want that limit to equal 0. So we have the limit as n approaches infinity. Uh-oh, kind of a messy looking infinity. N divided by n plus 14. So we can get each term and divide it by, why do I keep making messy infinity symbols? There we go. Divide each term by n. So n divided by n, divided by n, divided by n, plus 14 divided by n. We know this simplifies to 1, and this term simplifies to 1. So that gives us the limit as n approaches infinity of 1 divided by 1 plus 14 over n. Which is the limit of 1 is 1 divided by the limit of 1, which is 1, plus the limit of a constant divided by n is just 0. So we know that that limit is 1, which does not equal 0. Okay, so we need that first limit to be 0, but since it isn't 0, it fails the first condition. But since it failed the first condition, we always have a backup. So we know that by the divergence test, we can use that to find the limit. To find convergence or divergence. Okay, so we know that since the limit as n approaches infinity of a sub n equals some value that does not equal 0, in this case it equals 1, which is not 0, that means the series is divergent. right, any questions on that one? All right, anyone still writing? Okay. Go. Okay, so let's say for this example, we want to know for what value of P is the series, the sum from n equals 1 to infinity of -1 to the power of n minus 1 times 12 divided by 8n to the power of P convergent. Make that G a little bit neater. Is it P greater than 0 or P less than 0? And I believe they have a question like this, it would be multiple choice. Now with this one, you just want to remember your P series. So n equals 1 to infinity of 1 over n to the power of P. So if P is greater than 1, we know it's convergent. P is less than or equal to 1, divergent. And I'll separate those just to avoid any confusion. And I'll kind of put a separator across that whole thing. Okay, so by the first condition, the limit as n approaches infinity of a sub n, where our a sub n is 12 divided by 8n to the power of P. So that's the limit as n approaches infinity of 12 divided by 8 times n to the power of P. Okay, so we can see that this will only meet the condition if P is greater than 0. We're basically approaching infinity. Okay, so now we have to see with the second condition, well, we know our a sub n is equal to 12 divided by 8 times n to the power of P. Or if we wanted to, we could actually factor out that 12 over 8, which I'll do that just to make the next step a little easier. So that 12 over 8, we're just going to factor that out to the front and make this 1 over n to the power of P. doing that because now we can just make that our a sub n plus 1, 1 over n plus 1 to the power of p, and not have to worry about the coefficient. So we make that 1 over n plus 1 to the power of p is less than or equal to 1 over n to the power of p. Okay. And once again, we can see that this is true when p is greater than 0. Okay. So we can see that out of those two options, p is greater than 0 would make this convergent. Oops, there we go. All right. Any questions on that one? All right. Anyone still writing? All right. So now we're going to look at estimating sums of alternating series. So let's say if we know that some value s is equal to the sum from n equals 1 to infinity of negative 1 to the power of n minus 1 times our series a sub n, where we know that a sub n is greater than 0. And that represents the sum of our alternating series. So is the sum of our alternating series. Where you know that it meets the condition that a sub n plus 1 is less than or equal to a sub n. And the limit of a sub n as n approaches infinity is equal to 0. Okay, so if those conditions are met, then we know that the remainder of our series, we'll call that our remainder, is equal to the sum of the series minus the estimated sum. I'll make that s sub n. That's the sum minus the estimated sum. All right, anyone still writing? All right. So let's say, for example, if we wanted to estimate the value of the convergent series sum from n equals 1 to infinity of 10 times -1 to the power of n divided by 3n factorial. By adding the minimum amount of terms to ensure an absolute error less than 0.001. Okay. Well, since the previous conditions that had to be met shows convergence, plus they kind of tell us that it's convergent, so we don't have to worry about doing a test for convergence. The series converges. So here we pretty much know that it's just from that one given that the conditions are met. So we're okay there. We don't have to test each one individually. Okay, so this one, it's a little tedious. So, but we're going to plug in values for n is greater than or equal to 1 until you reach a sub n plus 1 is less than or equal to 0.001. And of course, that's where your a sub n, hopefully that's enough room, is equal to 10 divided by 3n factorial. Because that -1 to the power of n, we just factor that out to the front. Okay, so what if we plug in n is equal to 1? So our a sub 1. Oh, that's just 10 divided by 3 times 1 factorial. Well, 3 factorial is just 3 times 2 times 1. So 10 divided by 3 times 2 times 1. Plug that into your calculator, you get 1.66667 and kind of round it. Okay, so our a sub 2 is just 10 divided by 3 times 2 factorial, or 6 factorial. So that's just 10 divided by 6 factorial, just 6 times 5 times 4 times 3 times 2 times 1. Plug that into your calculator and you will get 0.013888889. approximately. So if you plug in n is equal to 3, that's 10 divided by 3 times 3 factorial. Or just 10 divided by 9 factorial. Okay. So that gives us 0.00002756. Which is really what we're looking for. Because we know that a sub 3, which is 0.00002756, is less than or equal to 0.001. Excuse me. Okay, so we know that the sum minus the estimate is equal to the remainder. And in this case, we want that remainder to be less than or equal to a sub n plus 1. Okay, so we know that a sub n plus 1, just kind of a note here. Since our, excuse me, our sub value is 3, that's just a sub 2 plus 1, which means that our n is equal to 2. So that means we have to take our series to 2. So take the series. So you have the sum from n equals 1 to 2 of 10 times negative 1 to the power of n divided by 3n factorial. Okay, so if we plug in n is equal to 1, we have negative 1 to the first power. Actually, let me write n is equal to 1 just to make sure it's able to be followed. So n is equal to 1. So we plug it right in. So that's 10 times negative 1 to the first power divided by 3 times 1 factorial. Plus 10 times negative 1 squared divided by 3 times 2 factorial. Okay, so negative 1 to the first power is negative 1. So that's negative 10 divided by 3 times 1 is 3, so that's 3 factorial. Plus negative 1 squared is positive 1. So 10 times 1 is 10 divided by 3 times 2 factorial, which is 6 factorial. Well, kind of looking up, we did that work already, so we're okay. So 10 divided by 3 factorial is just 1.66667. but it is multiplied by -1. So that's -1.6666. I'm going to match up decimal values. 1, 2, 3, 4, 8. 666666. 1, 2, 3, 4, 5, 6, 7. Or at least get it a little bit closer. I don't want this one to have too many more decimal values than the other. It will throw off the estimate. Okay, plus we have 10 divided by 6 factorial, which is 0.013888889. Okay, so we add those together, we have -1.652778. Okay, so this value ensures that the estimated area will be less than 0.001. And estimated area, not area, error less than 0.00. Make sure I have enough. Yep, 001. All right. Any questions on that one? All right. So we will go ahead and stop there. And tomorrow we will finish up with absolute and conditional convergence. Tomorrow is Tuesday. All right, you have a good one. You too.
Have a nice
All
day.
right, you have a good day too.
See you.
Mm-mm.